Hi guys, welcome back to my YouTube channel. And today we're going to be discussing the topic of isotopes and carbon dating. So let's get right into it. To start off with, what is an isotope? An isotope is an element that has a different amount of protons and neutrons. However, when the number of protons and neutrons are the same, it is called a stable element. Let us imagine a cut watermelon piece and call this as an atom. Each of these pieces could have several black and white seeds. For the time being, let's call the black seeds as protons and the white ones as neutrons. When you piece together all the separate pieces, it can form a whole watermelon, which in our case can be considered as an element. So we can sum our understanding and say that an element is a pure substance with a specific number of protons and varying numbers of neutrons and electrons. An atom is the smallest building block of matter. A proton is a positively charged subatomic particle, and a neutron is a neutral subatomic particle. As you can see in this diagram, protons and neutrons make up the nucleus of the atom. And in this case, this diagram is actually an example of an isotope since the number of protons and neutrons are different. Additionally, negatively charged subatomic particles called electrons orbit this nucleus. However, while discussing isotopes, we only need to focus on protons and neutrons, more specifically, the difference in their number. The periodic table consists of 118 elements, and now you may be wondering, out of all of these elements, how do you identify the isotopes? Let's take one example from here, carbon. In this example, 12.011 is the atomic mass of carbon. The atomic mass is the sum of the protons and neutrons, and each of them have a mass of 1 AMU. In this case, 6 represents the number of protons, so the number of neutrons is 12 minus 6, which is equal to 6, and the remainder is the electrons. Since the number of protons and neutrons are equal, 6 and 6, carbon is not an isotope. Then on the right over here, we have hydrogen. Based off of the previous explanation, 1 represents the number of protons, and since 1 minus 1 is equal to 0, this basically means that hydrogen has no neutrons. Therefore, we can conclude that this varying number of protons and neutrons make hydrogen an isotope. Now let's take hydrogen to study the atomic structure. Over here, you can see 3 isotopes of hydrogen, which each have 1 electron and 1 proton. On the left over here, you see an isotope that has 1 proton and 0 neutrons. Hydrogen 1 is the most common form of hydrogen, and it is this form that is found on the periodic table. It is interesting that the most commonly found variant of hydrogen is actually an isotope and not a stable element. Then there's hydrogen 2, which is the only form of hydrogen which is not an isotope, because in the nucleus you can see that there's 1 proton and 1 neutron, which means that the number is equal. Then the last variant of hydrogen is hydrogen tritium. In this, there are 2 neutrons and 1 proton, meaning that this is an isotope. Let's look at some isotopes that you probably know of and some less well-known ones. Hydrogen is the first element in the periodic table, making it the first isotope. Carbon-12, which is the carbon found on the periodic table, is not an isotope, but carbon-14 is, because it has 6 protons and 8 neutrons. Now moving on to some less well-known, but just as important isotopes. Technetium-99 is the most frequently used isotope in medical applications, such as medical diagnostics imaging scans, and it is used as a radioactive tracer for nuclear medicine. Americium-243 is used in smoke detectors, which are very important and useful household products. All isotopes are radioactive isotopes and are used in various different forms of everyday life. First, there's phosphorus, which is used for cancer detection and treatment. Then there's iron, which is used for anemia treatment. Anemia basically means a lack of red blood cells carrying oxygen. Iron helps in the anemia treatment because iron helps in production of hemoglobin, which is a molecule in your blood that carries oxygen. Then there's cobalt, which helps with gamma ray irradiation of tumors. When cobalt decays into nickel, two wavelengths of high energy gamma rays are emitted, which is why cobalt specifically helps with gamma ray irradiation. Then there's technetium-99, which helps in brain, thyroid, and liver scanning. And iodine is used in diagnosis and treatment of the thyroid function. This is because your thyroid gland uses iodine to make thyroid hormones, which can help control growth, repair damaged cells, and support a healthy metabolism. Xenon is used in lung imaging. While in lung imaging scans, you inhale the xenon gas to provide diagnostically relevant images of lungs to your physician. Lastly, gold sometimes helps with liver disease diagnosis. So now let's talk about the topic of carbon dating, which plays a very big part in isotopes. This is the remains of a wealthy man and his slave found after years of decaying in the Pompeii ruins. We are able to give concrete reasoning about these findings and date it correctly to their time period due to the phenomenon of carbon dating. Willard Libby was awarded the Nobel Prize in Chemistry in 1960 for his discovery of carbon dating. With this new method, we can estimate the age of any organic material up to 60,000 years. The theory is based on carbon-14, a naturally occurring radioactive isotope created when cosmic rays hit the air. It enters the food chain when plants absorb it through air and animals eat those plants. As the sun and atmosphere interact constantly, the number of carbon-14 atoms in your body is the same as in every other living thing. It's a constant. Then, every 5,730 years, half of it will decay. Using this information, we can date bones of mummies and Pompeian victims to an estimated age. Let's look at some more examples. Last year, scientists found 50 footprints stuck in the mud that were 1 million years old. How do we know that these weren't made yesterday by the neighbor's kid? How do we conclude about the timeline for something that's 1 million years and older? That's not quite as simple, but still possible. Using the same radiometric dating, scientists look at the layers of the Earth. As you go deeper into the crust, the fossils will have predictable levels of carbon-14. But once you get below, where there's not enough carbon-14, they look for other isotopes with longer half-lives, such as uranium-238 or uranium-235, which are all over the dirt of the fossils. Geologic data from tree rings, coral beds, and ice cores are examples where we take aid of other isotopes to date their age. Thank you guys so much for watching today's video, and if you enjoyed it, please drop a like down below and subscribe to my channel for more videos. Thank you. Bye.